Here we can start. So, hello everyone. Welcome to the post-contest discussion for Leetcode Biweekly 145. I hope you all had a good contest. Let's begin with the first question. So, the first question said minimum operations to make array values equal to k. In this question, we are given an array of integers nums and an integer k. This question defined an integer h to be valid if all values in the array are strictly greater than h and are identical. So for example, for this nums array 8, 10, 8, 10, 8, the integer h equal to 9 is valid because we have two numbers which are greater than 9, which are 10 and 10, and which are both equal. And what we're allowed to do is we had this one operation where we select an integer h, which is valid for the current nums array. And then we take all the numbers in nums which are greater than h and set all of them to h. So let's see this illustrated in this nums array. Right. So consider the first test case. Our nums array is 5, 2, 5, 4, and 5, and we have k equal to 2. So this is our first test case. Now, what the operation that we are given says that we could choose any number h such that for any number that is in nums. So let's just consider choosing x equal to 4. Now this is our nums array. So this is our nums array, and we have to see which elements, if we just consider the operation with h equal to 4, we have to see which elements in nums array are greater than 4, strictly greater than 4. Now we can see that 5 is greater than 4, 2 is not greater than 4, 2 is less than equal to 4, 5 is again greater than 4, and 4 is not greater than 4, 4 is equal to 4, and 5 is greater than 4. So basically, h is a valid number with respect to this array because all elements in nums that are greater than equal to h are equal. That is, 5 is greater than equal to h, 5 is greater than equal to h, and 5 is greater than equal to h. If we had another element, say 6 in this array, then even 6 would be greater than equal to h, and h would not be valid. So basically, consider a sorted array. So if you just consider this sorted array like 2, 4, 5, 5, and 5, then these are the elements which are greater than equal to h, which are strictly greater than h. So 5 is strictly greater than h, and there is exactly one unique element in this part of the array that is strictly greater than h. So that is why h is valid. So if, for example, h was, so if we consider h equal to 3, so if we had h equal to 3, now is h equal to 3 valid with respect to this array? Well, our array is 2, 4, 5, 5, and 5. And which elements are strictly greater than 3? Well, 2 is less than equal to 3, so 2 is not strictly greater than 3. 4 is strictly greater than 3, 5 is strictly greater than 3, 5, 5, and 5. Now, over here, we have two elements which are strictly greater than 3, that is 4 and 5. So, 3 is not valid. 3 is not valid. Basically, h is only valid when there is exactly one unique element which is uh, there is exactly one unique element which is strictly greater than h. And what we are given is that the operation we are given, it says that, for example, we have this array 2, 4, 5, 5, and 5. Now we can choose an valid edge. In this array, the only valid edge is h equal to, actually, every edge that is greater than equal to 4 is valid. But let's consider the value of h equal to 4. Now, when we consider the value of h equal to 4, which are the, this is a valid h value because every element which is strictly greater than h is only 5, and there is exactly one such element. So according to our operation, what it says is that okay. So what our operation says is that take this h equal to 4 and see which elements are greater than h. That is, here we have 5, 5, 5, and set all of them equal to h. That is 4. So our array, which is 2, 4, 5, 5, and 5, becomes 2, 4, and this 5, 5, 5, which is strictly greater than h, becomes 4, 4, 4, which is the value of our h. Basically, if you want to visualize this thing, you can basically just say that, let's just say that this is your x-axis, this is your first element, this is your second element, this is your third element, fourth and fifth element, and our array was like 2, 4, 5, 5, and 5. And what we are given is that the first element has value of 2, so it has a value of 2. The second element has a value of 4. Let's just say 4 is over here, so the second element has a value of 4. The third, fourth, and fifth elements have values of 5. Actually, we are considering the sorted array over here, so these have values of 5. So basically our array kind of looks like this. This is our first element, this is our second element, these are our third, fourth, and fifth elements. And what we can do is we can just kind of draw this line H over here. Now over here this H actually overlaps with this 4, but it's not compulsory. The only thing that's compulsory is that there should be exactly one type of elements over here. So if I have this line H and I draw this another line which is all the elements which are greater than H, and in the array, let me just use different colors for this. Basically, we have this value of H over here. So we have this value of H over here. Just draw a different graph beneath. So this is this is our array. The first element is 2, the second element is 4, and the last 3 elements are 5. The last 3 elements are 5. when we do an operation, we select an edge. So this is supposed to be a vertical, horizontal line. So when we select h equal to 4, basically we take this vertical line, and what we say is that all the elements which are above h, so these are the three elements which are above h, all of them come down to this line. Okay. Now in the next operation, what happens is, in the next operation, basically you have, in the next operation, our array transforms to, the first element is 2, the second element is 4, and the last three elements, which were 5, 5, 5, they have been brought down to this value of 4. So now 4 is the maximum element in this array. Basically, what our operation permits us to do is take an cutoff h, take a cutoff value of h. If this is our array, then basically take a cutoff value of h, like this is the h value, and bring down every element which is greater than h, which is above this line, all the way up to this line, right? And h is only valid when there is exactly one, like one such type of element. So I can have two or more such elements at this level, but it's not okay if I have like this element over here, like I have two levels which are above h. So basically h is only valid when I have one level above h. This is not a valid h, but something like this would be a valid h, right? And now the uh, query that we are given in the question is, the query we are given in the question is, I have this array and I want to convert all elements. I want to convert all the elements of the array. Want to convert all the elements to this value k. Okay. Now let's just visualize what our operations would look like for the first graph. So for the first sample test case, not the first graph, for the first sample test case, initially we are given the elements, like the one element is 2, another is 4, and the last three are 5. Okay. What we do is, in the first operation, we select a value of h equal to 4 and bring all these down to 4. Okay. And why can I do this? I can do this because there is exactly one level above h equal to 4. There are not two levels. I cannot do h equal to 3, because if I want to do say h equal to 3, if I want to do say h equal to 3, then I have this one level of 4 which is above h, and one level of 5 which is above h. So h equal to 3 is not valid yet. Then after I'm done with this, my graph will now look like, I have a 2 over here, I have a 4 over here, which is my second element, and my last three elements have been brought down to 4. Okay. Then next, what I could do is I could just select an operation of h equal to 2, and all these elements will be brought down to 2. And my final array will look, this is my first element is 2, second element is 2, third element is 2, and the final three elements also are 2. And since my k was equal to 2, all my complete array has been converted to 2. So if you look at this operation in terms of numbers, it will be like 2, 4, 4, 5, 5, and 5. You select h is equal to 5, sorry, h is equal to 4. Now 2 is less than 4, no change. 4 is equal to 4, no change. 5 is strictly greater than 4, so you can change 5 to 4. 5 is strictly greater than 4, you can change 5 to 4. 5 is strictly greater than 4, you can change 5 to 4. Next, you choose h is equal to 2, Well, 2 is less than equal to h, which is 2, no change. 4 is strictly greater than h, so change 4 to h, which is 2. Similarly, change 4 to h, 2, 2, and 2. Finally, you have this array which is completely been converted to k, which was indeed 2. Now, to get an intuition of what we want to do over here, basically, our graph would look something like this. The problem given to us is something like this. You have these elements. Now, again, I am considering these elements in an sorted sense. Okay. You have these elements and you have this value of k over here. You want to calculate what is the minimum number of operations I need to do to bring down all these elements down to k. Okay, I want to bring down all of these elements down to k. So I want to bring down this element down to k, this element down to k, this element down to k. Okay. Now, if there was no constraint on choosing the value of h, if there was no constraint on choosing the value of h, in the first go I would have chosen value of h equal to k, and I would have brought down all the elements down to h equal to k. But I can only choose a value of h when there's exactly one level above it. So this is my array, and this is my target. This is the target that I want to reach, that is k. Now, what are the permissible values of h where I can like draw a line for h? Can I draw a line over here? Yes, I can draw a line over here. There's exactly this one level above h. Can I draw a line over here? Yes, I can draw it. Like, let's just say that this matches it. So say this is 4 and this is something 7. Can I draw a line over here, which is say h equal to 3? No, I cannot draw this line. I cannot draw this line because there are two levels above this line of h equal to 3. So I can only draw a line up to 4, and I want to bring this thing down as fast as possible. I want to minimize the number of operations. So what our process would look like, if you just visualize what we are doing over here, what we are doing over here is we have these columns and we take the largest column, we take the tallest column and the second tallest column and set the value of h equal to second tallest column and bring the tallest one down to this height. So after this operation, basically the values of our column will be like this is my smallest, this is my second tallest, and my tallest has been converted to the second tallest too. And then I repeat this process all the way up to I get to my smallest element. When I get to my smallest element, all my columns are of same size. Okay. Next, what I have to do is I have to check. Okay, I am down to like my smallest element. Why do I want to get to my smallest element? Well, you see, if this is my array and this is my k, I want to bring down this column down to this, but I can't operate like I can't just set h to k and bring down this column because there is one more level above this column. So this is my first level, this is my second level. So I have to do certain operations to bring down this second level down to first level. I can't do that too still yet because I have this third level which I have to bring down to second level. So what I do first, I see this third level, I bring it down to the second level. I do one operation over here. Then I see this second level. The third level has been eliminated now. I have this second level and I have this first level. I bring down this second level down to my first level. I do one more operation. And then I have this first level which I want to bring down to k. So I do my third operation and I kind of have three operations. So if you basically kind of look at what we are doing over here, we just have a set of levels. And first we operate to bring them down to the smallest level. And then finally we check if we have to bring down the smallest level all the way down to k. In some cases, it may happen that the smallest column is actually lesser than k. In that case, we have our answer equal to -1. So basically consider the case of say k is equal to 3 and your array is 2 and 5. Well, 2 and like let's just consider more values 2 and 5 5. So if you consider h is equal to 3, you can have h equal to 3 because there is exactly one type of element, that is 5, which is strictly greater than 3. You have converted this to 3 and 3, but your 2 remains 2. Now in any scenario 2 can only decrease, but it won't increase, right? So 2 can only decrease, it won't increase. So if your smallest element is strictly less than k, it can't increase because our operation only allows us to decrease an element, not increase it, which implies that there's no answer. And so, according to the problem, you have to return a -1, right? And the other part of the process is you just look at all the different levels that you have available, that are available to you. You start with the largest level. You take the largest level, do an operation, reduce it down to second largest level. Then you take the second largest level, do an operation, reduce it to the next smallest, all the way up till all your columns have the same level. Then you check if you need to reduce it further, like if k is here, then you need to reduce the smallest level down more. Or in the other case, maybe the k is already here itself, so you don't really need to reduce it any further. Uh, are there any doubts? Okay. Right. I think there's someone who had like 525, 52545. Okay. So for this case of like 5254 and 5, and with k equal to 2, our graph will look something like this. Uh, your k value is 2. The first element is 5. Second element is 2. Third element is 5. Fourth is 4. And the last one is 5. This is your largest level. You reduce it down to the second largest level with one move. This is your first move. Then now this is your current level. Let me just represent it with different color. So this is your like the current largest level, and this is your next level. Okay. Then you do one operation to reduce it down to the next level. And all your columns are like of same level now. This is your first element, second element, third element, fourth element, and fifth element. And actually even k is at the same level, so you don't really need to do another operation right now. So all you need to do is two operations. In terms of in numeric terms, what this would look like is you would have 5 4 5 2 4 5, something like this. First, you choose h equal to 4, the second largest level, which will convert it to 4. 5 is greater than 4. Then 2 is less than equal to 4. 4 is less than equal to 4, so unchanged. 5 is strictly greater than 4. It will be changed to 4. In the next operation, what you will do is we'll take the second largest level, which is 2. So we take h is equal to 2. Or 4 is strictly greater than 2, so it will be reduced to 2. This 2 is less than equal to 2, so it will remain unchanged. Similarly, last two 4s will be reduced to 2. And we have all the elements equal to the smallest element. Now, since all the elements are equal to smallest element, we can now even change the smallest element. And we can see how much we have to reduce the smallest element to make it reach to k. But as we can see that k is 2 and the smallest element itself is 2, so we don't need to do an operation. In case that say k was 1 instead of 2, so instead of 2, say that the k was 1,
In that case, we would have to do one more operation, say h equal to 1, and then all our array would be converted to 1, all ones. Okay. That was the basic idea behind problem number 1. Can we just count the number of elements which are greater than k? And if any element is, so if any element is less than k, we'll return -1. About counting the number of elements which are greater than k, we actually need to consider only the unique elements which are greater than k, not all the elements. So if we just count it, like we will be counting 5 and 5 twice, so that won't be valid. Now, moving on to the code for this problem. First, we sort the nums array. Okay. Next, we do this check, like, is the smallest element in nums, that is nums of 0 in the sorted array, is this strictly is this strictly less than k? If this is strictly less than k, so for example, if we had, this is 2 and our k is 3, 2 can never be reduced down to 3. So if this was strictly less than k, then return -1. There's no answer. In all other cases, what we do is we count the number of unique elements in nums array. How are we doing it over here? We are basically checking if two adjacent elements in a sorted array are different. If I were to tell this to you in terms of our array, so consider our array like this is 2, 2, 3, 3, and 5 and 5. So this condition, like nums of I minus 1 is not equal to nums of I, will be triggered exactly at these junctions. So 2 will be okay, 2 will be okay, and 2 and 3 are different. So you have one triggered of this condition, that if condition, then 3 will be same, like, and 3 and 5 are different. So you have one more trigger of this condition, and 5 will be similar. So basically what we are doing over here is how many times is my level changing. So this is basically counting, okay, I start at 2, I start at 2, 2. My next element is 3. Okay, my level has changed. So I have to do one operation to bring down this level in some part of my process. Okay. Then my level remains 3, and then my level becomes 5. So I need to do one more operation to bring down this level to this level, and then I can bring down this whole level to the smallest level, and so on and so forth. Basically, this if statement is checking how many times is my level increasing, and those many times I have to do at least like for each level change I have to do one operation to bring down that level to the previous level. And finally, this statement checks that, okay, I have brought down all of my like elements. Like initially this was my element, these were my elements. So this is like first element, second element, third element, fourth element, fifth and sixth. I did one operation, brought everyone down to this level. I did one more operation, brought everyone down to this level. Now, is my k equal to 2? If my k equal to 2, then I'm done with my all the operations. Like I have the array that I needed. But if I have k equal to say 1, then I need to do one more operation and bring down this whole level down to over here. So this basically checks if the nums of 0, that is after these many operations, like after this whole loop, my complete array will be converted to my smallest element. Then is my smallest element equal to k? If it is, then I'm done. If it's not, I have to bring it down, like bring down the level to the smallest, to the k. Then that will require one more operation, and finally we just return a result. Speaking of the time complexity, so time complexity, as you can see over here, we are actually sorting our array. There are a few different ways to do this thing. You could use sets. You could use sets to count the number of unique elements in the array, and then check this condition, is the smallest element not equal to k or not equal to k. This whole operation is kind of counting the number of unique elements in the array. So speaking of time complexity, like this sort function takes big of n log n time, where n is the size of our array. The nums of 0 less than k, like all this is O of 1. This loop takes big of n time, and is your size of array, and this take O of 1. So overall our time complexity would be big of n time for the big of n log n time. So the n log n time is for this sort function, sorting things n log n time, and this take big of n time. So this will overall be big of n into log n. And the space complexity would be big of 1 because we aren't really using any other space other than the nums array which is given to us by default. So that was overall about the first question. Did- Okay, a few people have indeed used sets. Okay, so that was our first question. Now let's move on to the second question. The second question said minimum time to break the locks. In second question, well, we had a story. Bob is stuck in a dungeon, and to break out of the dungeon, he has to break n locks. Each lock requires some energy to break the lock. Okay, and they have given us an array, which is the energy required to break the ith lock. It is given by strength of I, and initially the Bob has a sword, and that starts with energy equal to 0. So initially you have 0 energy. Now you have this factor x, which is initially 1. So every minute, what happens is your energy increases by x. So initially x equal to 1. So every minute your energy increases by 1. Initially your energy is 0, at minute 1 it becomes 1, at 2 it becomes 2, 3, and so on. And if you break the ith lock, okay, if you break any lock, what happens is your energy is reset to 0 and your factor x increases by a given value of k. What you had to determine was what is the minimum time required to break all the n locks and escape the dungeon. Let's take the one example.
ब्रूट फोर्स अप्रोच लगा रहे हो ये होता कि हमने तुमसे कहा कि कैलकाटा यूनिवर्सिटी चले जाओ जैसे बताया तुम वैसे ही चले गए दिस इज ब्रूट फोर्स अप्रोच लेकिन तुम कैसे किए तुम गए इधर से तनकर होते हुए एक चाय पिए रास्ते में कॉफी पिए सुपर टेक होते हुए अंदर से घुस गए जाके दिस इज लॉजिकल कुछ समझ में आया
So moving on to the first sample test case, like we have the nums array which is equal to 3, 4, 1, and the value of our k is 1. So what this says is that you have 3 locks which have strength. The first lock has strength of 3, the second has strength of 4, and the final lock has strength of 1. Now consider like this is your sword, okay, and this is your x, that is the element with which you are incrementing. Yeah, initially it is equal to x. Initially your sword has strength of 1. All right. What happens? This is at 0th minute. Okay. So if you look at time, this is at 0th minute. On the next minute, which is minute 1, your sword strength, that is 0, increments by a value equal to x. So your x is 1, your sword strength is 0. So 0 plus 1 is 1. Okay. And your x remains the same for now. For now, your x remains the same. And let's just say you're trying to break this lock, the lock which you're trying to break. The first lock that I'll try to break is lock number 1. So in like my sword cannot break this lock right now. So I have strength of 0. So I don't do anything in the 0th minute kind of. In the first minute, my lock has strength of 1 and my sword has strength of 1, and basically my sword has strength required to break the lock. So I break the lock. I break lock number 1. Now, two things happen when I break lock number 1. First, my strength is set to 0. Okay. My strength becomes 0. Next, the value of my x, that is 1 is incremented by k. Now k is given over here as 1. So 1 plus k, that is the value of my current x, will become 2. So x becomes 2. Okay. And let's just say that the next lock that I'm going to try to break is, say, 3. I think according to, yeah. Or say 4. I want to break the lock number 4. Now, I want to break the lock with strength of 4. In the next minute, what happens is I have this strength of 0 and I have this x value increment of 2. So 0 plus 2 is 2. My x value has been updated to 2. So this is 2. Is my strength 2 enough to break my lock of 4? No, I cannot break lock of 4 with a strength of 2. Like I cannot break lock with strength requirement 4 with sword of strength 2. Then I go to the next minute without breaking this lock. In next minute, what happens is my current strength is 2, my x increment value is 2. So 2 plus 2, my next strength of sword will be 4, and my x remains 2 for now. In this step, my sword has a strength of 4, and when my sword has a strength of 4, what do I do? I have my sword has a strength of 4. My lock requires that I have a sword of strength at least 4 to break it. Then I break the lock. So I break the lock with strength of 4. Again, when I break the lock, although all those things happen, like when I break the lock, my strength resets to 0. So 4 becomes 0. And my x value increments by k. My k is 1. So this becomes 3. In the next minute, now I'm going to break the only remaining lock, which is 3. In the next minute, my strength was 0 and my x value was 3. So the next strength will be 0 plus 3, which is 3. And my k value is now updated to 3. And 3 is enough to break the lock. So basically, I break it, which is 3. And this was the time I required. That is, my time is equal to 4. And this was what you had to calculate. So what is the minimum time? What is basically minimum time is minimum number of such steps to break all locks. Right. So basically, we have to calculate the minimum number of steps that we have to go through to break all locks. First thing that we should like consider what is happening over here. Okay, so first what we are doing is even in this case, if you look at like what we are doing or in this 2 steps. Okay, so I have this lock that I want to break. It has a strength of 1. This is my lock strength, and I am having this x equal to 1. This is like my increment value, and my strength will kind of start at 0. I am first waiting for my strength to go all the way up to my lock strength. So I am waiting for my 0 to become 1. So at time 0, I am at 0. At time 1, I go to 1. Let's just say that our log strength was 3 rather than 1. Then I'll wait for like, this is my time. At time 0, my strength is 0. At time 1, my strength becomes 1. At time 2, my strength again increments to 2. At time 3, it increments to 3. So first, I have to wait for my sword strength to become greater than equal to log. Okay, so the first part of breaking a lock is waiting for the sword strength to become equal to lock. Then I break the lock. This is where I basically break the lock. And over here, my strength once again resets down to 0. Okay, so my sword strength becomes 0 over here. And then I repeat this process for a new lock. So if you kind of look at what happened over here, uh, my initial lock was 1, then we broke the lock 4, then we broke the lock 3. So for lock number 1, this is my time. So time is 0, 1, 2, 3, 4. And so for lock number 1, I first waited over here. My strength became 1. Then over here, I broke my lock number 1. Then actually, what happened over here was that when I broke my lock number 1, my strength went down to 0. And in the next stage, my the x value over here, which was 1 plus 1, 2, that was incremented into my sword strength. So if I were to, like, it's kind of getting confusing. So, okay. Let's see that what our sword strength was. So initially my like time is 0, 1, 2, 3, 4, and my sword strength is 0, 1. Over here I break my lock and my strength becomes 0. In the next stage, what happens is, in the next stage, and my x is equal to 1 over here. So x is equal to 1 over here. Over here x is equal to 2. In the next stage, what happens is, this is my 0. In the next stage I get 2. Then in the next stage I get 4. Then again I break my lock. After I break my lock, my strength resets down to 0 and x increments to 3. Okay. And over here, once again, I get my increment value, which is 0 increments by 3, and my sword strength becomes 3, and my final lock has a value of 3. So I break the lock. So basically, as you could see over here, I have waited for this interval. I have waited for this interval. I have waited for this interval. And in this interval, like at this point, I have broken lock with value of 4. At this point, I have broken a lock with value of 4. At this point, I have broken a lock with value of 3. So the process of breaking any lock is, first wait for like when you're breaking ith lock. Okay, so I was breaking locks in the order 1, 4, and 3. And so x for my 1, x was equal to 1. And my k is equal to 1. So when I break lock number 1, my x becomes 2. When I break lock number 2, that is 4, my x becomes 3. So if I have decided the order in which I am going to break the locks, then I can kind of calculate the amount of time that I am going to require to break these locks. Okay. And how do I minimize this time? So what I do is, I have this value of x. For each lock, I say that my sword strength starts at 0. At the next step, it becomes x. At the next step, it becomes 2x, then 3x, then all the way up to something k times x. So I wait for this much amount of time, and over here, I decide that I'm going to break my lock when my kx becomes greater than equal to the lock strength. Okay. And what is this interval? So what is this amount of time? Like, what is this 0, x, 2x? Up to where do I have to wait? What is this kx value? So we want to find like the minimum value of k. Uh, is there any answer? Okay. So basically what we want to find is, what is the minimum amount of time that I have to wait so that I can break the lock. Now, remember, over here, I have decided the order beforehand. We'll see how order affects the answer that you get. But let's just say that you have decided that I'm going to break my locks in like this order. First, I'll break lock with value of 1, next 4, then next 3. And I'll break them in this order. For them, I know that for this lock value, for lock with value of 1, x is equal to 1. For this is 2. And for this, it is 3. Now, consider we are breaking the lock with value of 4. Then first I have 0 strength. Next I have to wait like I wait for one moment and my strength goes up to 2. I wait for next moment, my strength goes up to 4. So 4 is my kx. Okay. Basically, what I'm saying is that what is the minimum value of k into x such that it is greater than equal to the log strength, that is the strength of I. That is the log strength. And we can just manipulate this equation in this way. So let's just say that k into x is greater than equal to strength of I. Strength of I is basically the strength of the ith log. Then you can say that x is greater than equal to the strength of the ith log. I'm just simplifying, shortening it to str divided by k. So basically this k goes down over here. And in terms of integer, like you could then say that the minimum value of x, sorry, it's not k. So sorry, we don't need, so our x is fixed, we need k, and we can say that the minimum value of k is this, and the minimum value of k is this upper bound of strength of I divided by x. What does this k signify? Well, this k says that what is the minimum time you have to wait for strength, for the sword to reach strength of I. Okay, so in our case, our lock had a strength of 4 and our increment x was 2. Then we had to wait for the first time. In the first time, we had to wait at strength of 0. Then our strength became 2. Even 2 was not sufficient. So we had to wait for 2 times. So we had 2 increments. This was our first increment. Then this was our second increment. So this is like 2 into 2 is equal to 4. In case our log strength was 5, then we would have to wait for one more moment where we went all the way up to 6. In that case, like we had k value equal to 3 into 2 is equal to 6, which is greater than equal to 5. Now, given that we have a fixed order, so if we have decided the order in which we are going to break the locks, and we are calculating what is the minimum time that I will require to break these locks, given that I am doing it in this order, I can calculate this value, like this is like 0, and the first I wait for one moment and then I break my lock over here for the first guy. Then for the next guy, I have to wait over here. This can overlap with the breaking of lock 0. Then here my strength becomes 2 and here my strength becomes 4. I break my lock. Then for 3, I wait over here. My strength is 0. It becomes 3 and then I break my lock. Okay. In a kind of way, what you could see is your answer is the summation of all these keys. That is all the amount of time that you have to wait. I hope this is clear. It's just confusing. Okay, how do we decide the order of locks? So the order of locks is something we'll come to in a moment. If this is clear, like I'll just summarize how we are going to, given a certain order, how we are going to calculate the minimum time that we require to complete this order. So first thing is for the ith lock, what is the value of x? Well, the value of x is, so I am at this, say at this third lock, then basically for third is with 0 based indexing, you have I is equal to 2, that is 0, 1 and 2. Then I have had two more locks before me. So for the ith lock, considering 0 based indexing, I have had, like, one was my starting value and I have broken I locks to reach over here. So I get I into k increments to my x. So for example, if you start at 1, this is my value for the first lock. Then when I break my first lock and go to my second lock, so for I is equal to 0, I have this value of x. When I break my first lock and go to my second lock, say k is equal to 2, then this becomes 1 plus 2, that is 3, and my value of I is 1. For I is equal to 2, this becomes 1 plus 2 into 2, that is 4. Like I add one more 2, this becomes 5. So for the ith lock, value of x is equal to 1 plus k into I. Why this? Because you have broken I locks to reach over here, assuming zero-based indexing. And so you have had k increments to x. So this is your value of x. Now what is your wait time? So what is this 0, x, all the way up to, okay, I think we had a bit of duplication in our notation, but okay, what is this k into x? So this k and this k is supposed to be different, but we have used k, so I just continue using this k, but it's different. So what is this? Given that you have this value of k, what is the minimum number of steps that you have to wait? So like what is kind of the size of this interval, size of this value of k? Well, this k is going to be the upper bound of what is the strength that you need, that is your strength of I divided by what is the value of x that you have. And in C++, since you only have lower bounds, you could have strength of I plus x minus 1 if you want to do it in terms of integers. Like this is how you would write it in code if you're using lower bounds, but this is what we are considering over here. So this is the strength of I, kind of like this is like 0, 1, 2, all the way up to k into x. So this is the size of this interval, this upper bound of strength of I divided by x. And this 0 can overlap. So basically we can have 0, 1, 2, break the lock, then 0, 2, break the lock, 0, 3, break the lock. And the first time moment is calculated as 0. So you kind of have this one moment, then this one moment, and then this one moment. So for a given order, your answer is actually summation of upper bounds of the strength of I and the x value of I. So this is like from I equal to 0 till n minus 1. For the ith element, the value of x will be 1 plus k into I, because you have broken k locks up to this point. Okay, so same order not believable. Okay. Like this was for calculating the answer for a particular order. Now, one thing that you'd see in the constraints for this problem is that the value of n is at most up to 8. So what you could do is you could just calculate the answer for all the 8 factorial permutations of your nums array. Right. So what we have is this is the answer for a particular answer. This is like this is the minimum time for one permutation. Okay. This is the minimum time for one permutation, and you have 8 factorial permutations. Like what is 8 factorial? 8 factorial is roughly around 5,000. So like, n can be at most 8, and it will have like 8 factorial different permutations, and 8 factorial is around 5,000. It's a bit larger than 5,000. And yeah, so 8 factorial is around 5,000. So you have 5,000 permutations to check. You can check each permutation in big O of n time, and big O of n is like n is less than equal to 8. So you'll have to check each permutation which is size of at most 8 in n factorial such permutations, which is about 5,000. So this will still be around like 10 raised to power 4 or 10 raised to power 5. Actually 10 raised to power 5. This will be like 4 times 10 raised to power 4, which is less than equal to 10 power 5. So this will still fit in the constraints. So if I just were to show you the code to clarify this, Basically, what we're doing over here is, first we sort our strength array. This is our initial permutation, like the sorted array. Then we calculate the min time. And this calculate min time function is what we discussed up to this point. What we are doing over here is, I'm going to break the ith log now. What is the value of my x? What is the x value? My x value is, initially my x started with 1, and I have broken I logs up to this point. So I have had k increments to x. So my x is 1 plus I into k, because I have broken I logs up to this point. And I have to wait for the upper bound of strength of I divided by x, which is represented this way in code, time for my sword strength to reach this point, and then I can break my log. So this is kind of like the representation of this summation. Okay, like this is this value in code is the representation of that summation, this for loop, and this is the minimum amount of time that I'm going to take for this permutation of strength, and I return this time. And what we are doing over is, we are just iterating over all the possible permutations of strength of I. Now the length of strength of I is at most 8. 8 factorial is around 5000. So this loop will run around at most 5000 to say 6000 times. And this complete function will run in, like, this will run upon 8 elements. So your total number of operations will be bounded by around 10 raised to the power 5 number of operations. And if you say talk about the time complexity for this code, the time complexity is big of, well, how many permutations are you checking? You are checking n factorial permutations. And how much time does checking each permutation takes? It takes big of n time. So your total time complexity is kind of n into n factorial, which is more or less big of n factorial. And speaking of the space complexity, well, you aren't actually using much any space at all, in fact. So your space complexity is still big of 1, but your time complexity is n factorial. And this code only works because the value of n is like fairly small, very small actually. So yeah, that was about this code. Yes, it's brute force. So is there any other strategy for this? Well, I couldn't think of any better strategy for this one. If someone could, please do share it. But like one possible hint to your answer would be like, you need at most like strength of I divided by your x time. So maybe we can use some dynamic programming, but I couldn't do it at the time of contest. If I do find any better strategy, I'll definitely share it. But like for now, this was it. A few people have tried doing this with backtracking and recursion and backtracking. I saw a few solutions that use recursion and backtracking, but I think overall, like, this is the basic idea. Basically, you sort the first array, you take then you explore all the permutations of this array. You basically generate all the permutations. Then for each permutation, you calculate the minimum time that you require to break all the locks with this permutation. And finally, you take the minimum of them, and that's your answer. So that was about problem B. Now moving on to the the third problem. This was the digit operations to make two integers equal. Before that, like, do we have any? Okay. So the third problem is digit operations to make two integers equal. In this problem, we are given two integers n and m. They consist of same number of digits. So this was given. And we can perform these operations any number of times. First, we can choose any digit from n that is not 9 and increase that digit by 1. Or we can choose any number from n that is not 0 and decrease it by 1. Then after doing this operation, n must not be prime, else this is not a valid operation. and even the original values of x cannot be prime. And basically we have to do this operation any number of times and make n is equal to m. And the cost of each the total transformation of taking from n to m is the sum of values of all the numbers that you have encountered. And if you cannot convert n to m after any number of operations, then just return -1. So this is the definition of prime that they have given. And yeah, let's consider the test case. So actually the test case that they gave is kind of too big. So in the sample test case, like they have given 10, you have to convert 10 to 12, and it requires 85 operations. So 85 is a bit too much. So I'll consider a simpler test case. So you're going to convert 10 to 51. Okay. So you're going to convert 10 to 51. Or let's just consider even a smaller operation. You're going to convert 10 to 21. So first thing, you start with, you have been given n equal to 10, m is equal to 21. Now you start with n is equal to 10. You choose one digit. So let's just consider the first digit. My digit is 1. What I can do is I can increment this digit to make it 2, or I can decrement this digit to make it 0. So my 10 can go to 20, increment this digit, or 0, 0, which is basically 0, decrement this digit. Or I can choose my second digit, which is 0. Now for 0, I cannot decrement it because it is 0, otherwise it will go into negative. But I can definitely increment it. So 0 plus 1 is 1. So from 10, we can go to 11. But we're given the condition that no number in the complete cycle should be, like in the complete process, should be a prime number. 11 is a prime number, so we can't go to 11. Okay. Now I have 20, I have 0. Well, 0 is kind of very far away from our target of 21. So we let's operate on 20. From 20, I have like these digits. So my first digit is 2. From 2, I can go to 3, or I can like increment it and go to 3, or decrement it and go to 1. So from 20, I can go to increment 2, go to 30, decrement 2, go to 10. That is where I came from. Or I have the second digit, which is 0. Again, I cannot decrement this guy because that will make it go to negatives, but I can increment it to make it go to 1. So from 20, I can go to 30, 10, or 21. So if I were to represent this, from 10, I could go to the like this digit. If I increment 0, I could go to 11. If I incremented 1, I could go to 20. I decremented it, I could go to 0, 0. 11 was prime, so this was not valid. We didn't consider it any further. For 20, from 20, I can go to decrement this 10, increment this 30, take this 0, we can increment is 21. 21 is my final goal, so I can trace this path back. I have 10, 20, and 21. And this is like kind of my answer. So my answer over here is, so for this complete transformation, my answer is 10 plus 20 plus 21. According to the problem, the total kind of cost of all your operations is all the integers that you encounter in those operations. So for this, I first converted 10 to 20. I incremented the first digit. Then I converted 20 to 21. I incremented the second digit. And the total cost of my operation was 10, 20, and 21, the sum of all of them, which is 51. Now, what we had to do over here is we were given this numbers n and m, and we basically had to find the minimum cost that I required to go from n to m. So from n, I go to something, then I go to something, and all the way up to m. And I can also have multiple paths over here. And I want to find the minimum cost to convert n to m. But let's just say for now, we are trying to reach to m from n. Okay. And if you actually look at it, it's a graph in a sense. So if I say that this was my value of 10 initially, let's represent this 10, the value of 10 by a node, and consider what does each operation do. So I can convert 10 to 20 by incrementing the first digit. I can convert 10 to 0, 0. I can convert 10 to 11. Well, 11 is not a valid node, but just for once consider it. And I can also similarly convert 20 back to 10. So basically this is a bidirectional graph. Rather than representing these arrows, just consider a simple bidirectional edge. So what I have is a bidirectional graph, and what I want to do is I have this graph, and this graph can have like any number of nodes and edges, and I want to find what is the path, like the sum of whose nodes is minimum, a path which connects n to m and the sum of whose nodes is minimum. And that's a very, let's just say, a bit of kind of a difficult problem to imagine. So rather than doing that, uh, let's consider something simpler. So I'm starting at this 10. I can go to 20. I can go to say 0, 0. Then from 20, I can go to 21. Let's assign this edge a weight of 10. So let's just say that I need a cost of 10 to go from 10 to 20. I need a cost of 20 to go from 20 to 21. Okay, why do I assign a cost of 10 to going from 10 to 20? You have to convert n to something, then you have to keep on converting these things all the way up to all the way up to the point where you reach the value of m. And finally, you have to add up all these things. Now, in the most optimal scenario, it never makes sense to go back to certain point. Okay, you started over here, this was your n, this is your m. You are over here, you went over here, then you from over here to over here, you went over here. It never makes sense to go back and then loop over it if you want to have an optimal answer in which you minimize the total cost. So in that case, basically what you want to do is, how do we assign, like what we are trying to do is we are trying to convert this whole problem into something that's in a sense a known problem. And in most cases, like you try to optimize the distance from or between two nodes in terms of their edge weights and not the node values. And what we want to do is we want to basically uh, convert this problem where we have these node values, that is 10, 20, and 21, into something that is edge weights. Okay. So for example, what we are saying is, for now, ignore this value of 21. And from 10, I'll start exploring from 10. Okay. I'll start exploring my graph from 10. And for each of the edge I find, I'll assign that edge a value of 10. Now over here, I reach my node with value of 20. So let me just draw it in a better way. So I start from my edge of 10. So I reach 20, I reach 11, I reach 0, 0. And I assign all of these edges value of 10. 8, 10, 7. Okay. So assign all these edges a weight of 10. Then from 20, I need to move forward. From 20, I can move to 21. From 20, I can move to I can move back to 10, but I won't consider that. I just need to move to new values which haven't been explored, and I can move to 30. And I say that the cost of moving to these new avenues is 20. And if you actually consider what is this cost, like this is 10 plus 20. So what I'm saying is, to reach 21 from 10, you need this 10 plus 20 cost. Like you need to go through these integers and then you will reach to 21. This is what these edge weights mean. Again, why are we trying to assign edge weights? Because once you have edge weights and once you have converted your problem, like your graph problem, into a problem of minimizing the uh, cost of path in terms of edge weights, you can use certain standard algorithms which will be easier to implement. So to recap, kind of, we have been given n and m. What we do is we represent each number as a node. Then we start at n and basically we kind of do a breadth first search in a sense and go on assigning values to edges, like edge weights. So if I say over here, so I'm at 10, then from 10 I can go to 20, I can go to 11, 0, 0, I can also go to 0, 0, but I just won't consider it for now. 11 is a prime number, I don't really go anywhere forward. From 20 I can go to 30, I can go to 21, I can also go back to 10, but I won't consider that. So from going from 10 I get edge weights of 10, 10, 10. Going ahead from 20, I get edge weights of 20, 20. From 30, I can go to 40, and I'll say that this incurs a cost of 30. From 30, I can go to 31. This incurs a cost of 30. From 21 to, I can go to 31. And yeah, actually over here. So from 21 to, I can go to 31, which incurs a cost of 21. And from 21, I can go to 22, which say incurs a cost of 21. And this is, let's just say now, actually 31 is a prime number, so we won't be like in the problem. If we go by the problem, 31 shouldn't be considered. But let's just say that we wanted to reach from 10 to 20, and for now forget that 31 is a prime number. What will be my cost to reach 31? Okay, according to these edge weights. So this is 10, 20, then 30. So I can reach 31 in one way, that is 10 plus 20 plus 30, that is 60. One more way in which I can reach it is 10, 20, and 21, that is 10 plus 20 plus 21, which is 51. So the minimum of these two is like 51. And if you actually trace back this path, you're going from 10 to 20, you're going from 10 to 20 to 21 to 31, and your total edge weights actually consider these things and give you 51. And if you calculate the cost of this whole operation, you have to calculate the sum of these numbers, which is 10 plus 20 plus 21, this is 51 plus 31, which is 82. You can just say that this is 31 plus the all the cost that I required to reach up to here, which is 82. So sort solution section. Okay. Like if I have to recap, basically what we're trying to do over here is we have we are representing each number with a node in a graph. We every time we can go from one node to another node, we are representing it by a bidirectional edge, and we are basically saying that the node closest to the source, that will form the weight of this edge. So from 10, like I have an edge of weight 10, 20, 21, and so on and so forth. And if I have like one more way to reach this 21 element, like I'll construct this graph, and then once I have constructed my graph in this way, my answer would be 21 plus the minimum distance of 21 from my start point. The minimum distance from my start point. So if I have to say it in a general way, what will happen is I'll start at n, then I'll have this edge with a weight of n, then I'll end up at some first number like n1, then I'll traverse to the next number that is n2. This will have an edge of weight n2. Then I'll go to n3. This will have, okay, sorry, this will have an edge weight of n1. This will have an edge weight of n2. And finally, from n3 with an edge weight of n3, I'll at the end reach a node which has a value of m. And so the total the minimum distance of m from n is n plus n1 plus n2 plus n3, the sum of these edges. So this is the minimum distance. And what I can do is, once I've calculated this minimum distance, I can just say that my final answer, in my final answer, I have to calculate the total cost of transformation, which is n1 plus n2 plus n3 and plus m. What I can just say is, okay, this is my minimum distance of m from n in my graph, and in that I just add m, then I'll get the answer that I need. So what I've done is I have changed my problem to calculating the minimum distance of m from n in my graph. So this was like the major idea behind solving this problem. Like first you calculate, first you represent the problem as a graph. You represent each number as a node in the graph. Then for each transition, you consider the edge and you appropriately assign weights to that edge. And there are multiple ways to assign weights to those edges. What I said was like one of the possible ways. But basically what you have to do is you have to assign it in such a way so that you can use the minimum distance of n from m and do some operations to it. Like the whole idea was convert the problem to a graph, like a graph representation, and somehow we had to like have this minimum distance from n to m, and we can apply some operation over here, it's plus m, and get our answer, that is the sum of all values of n that you need to get your that you need to transform from n to m. And in our case, this was our graph, and the way we assign the edge weights is we start from n, we assign all the adjacent edges the weight of the current node, and go ahead, so on and so forth. And now our problem is reduced to, so our problem is reduced to, what we have right now is we have a weighted bidirectional graph. So we have a weighted bidirectional graph, and we have a node n and a node m, and we have to find the the minimum distance, or like not even minimum distance, basically like the minimum weight of a path from n to m. And the standard algorithm to do this is the Dijkstra's algorithm. So what we do in the Dijkstra's algorithm is, let's consider the test case that we were considering over here, that is 10, 20, and 21. And this is our n node, this is our m node. In Dijkstra's algorithm, we just say that, okay, I'm starting at n. Initially, my n has a distance of 0 from itself. Then let's just say that we have these 3 edges. Say that this edge has weight of 4, this has a weight of 7, this has a weight of 5, and this has a weight of uh, 5 too. Okay. And what we say in our Dijkstra's algorithm is, initially the first element, this element that we start from, has a distance of 0 from itself, and all the other nodes have distance of infinity from the first node. And we are going to do is, we are going to calculate the distance of each node from this start node, the start node, that is n. Then we look at the node with minimum distance, that is 0. So we have this node. So this is our graph. This is, I have 5, 5, I have 4, 7. Now this is my node with a distance of 0 from itself. I take this node and update the distances of all the nodes that are adjacent to it. So this is a distance of 0. This was previously at a distance of infinity, and now it can be like 0. From 0, I can go to this node. So 0 plus 4, the cost over here will be 4. And I take the minimum of infinity and 4, which is 4. Then I update this node to, like, I could reach this node with cost of 0. From 0, I take cost of 5 and reach here. So 0 plus 5 is 5. Previously, it was infinity. So the minimum of 5 and infinity is 5. And so this is after my update. So after my update, my graph becomes something like, the first node is at distance of 0 from itself. This is at distance of 4, 5, and this is still at a distance of infinity. So this is 4, 7, 5, and 5. And what I do is, I take the, so like this 0 node has been explored, so I don't really need to do anything else to it. I take the next node which has not been explored and which has the smallest distance. So as you can see, it is 4 in this case. So I take this node and I go on updating all of its neighbors with with the minimum distance from the source. So I'm at 4 over here. I can traverse this edge and go to here with 4 plus 4, like cost of 8, but this is already 0, so I don't need to update it. I can come over here, like have this 4 value over here right now. I can traverse this edge, do 4 plus 7, that is 11. So this is infinity right now, and the minimum of infinity and 11 is 11. So my graph will become 4, 7, 5, and 5. This is 0. This is 4. This will become 7, and this will become 5. And these two nodes have been visited, so they don't need to be considered. Then I take the next smallest node, which is 5, and I update its adjacent nodes. Again, I can use this edge and traverse this edge to do like 5 plus 5 is 10, but 10 is greater than 0, so I don't need to update this node. Then I can traverse this edge, say 5 plus 5 is 10. Sorry, this is not 7, this is actually, this has to be 11. So this would be, this would be 11. So, and I would have like 5 plus 5 after traversing this 5. 5 plus 5 is 10. So the minimum of 10 and 11 is 10. And I've also visited this node now. Now my graph will look something like, this is 4, this is 7, this is 5, and 5. And all these nodes have been visited. And my distance values are, like, this is at distance of 0 from itself. I can traverse this edge, go over here with cost of 4, traverse this edge, go over here with cost of 5, traverse this edge, go over here with the cost of 10. Finally, you can also visit this node, but it won't change anything. But your final cost is kind of 10. And in this problem, like this will be our minimum dist, and in this we'll also add our m value if this was our m node. So 10 plus m would be our answer in this case. And that's how like your Dijkstra algorithm proceeds. In Dijkstra's algorithms, you maintain either you maintain a visited array, or in case of priority queue, you basically maintain a distance array. What you do is that in each step, you choose the u with minimum value of distance from the start, which is usually represented by a distance array, that is distance of u. Initially, your distance of start node, that is in our case n, is 0, and distance of all other nodes is infinity. We just set it to some large number. And so we take this node, update its neighbors, and then just continue this process until all the nodes are marked in a certain sense. So that was the whole idea. And let's move on to the code. So yeah, one more thing that we didn't discuss was that in this whole scenario, like in this whole thing, we are going for 10 to 20 to 21. There's actually one more path over here, that is 10 to 11 to 21, which actually has smaller cost, that is 10 and 11. But according to the problem, we can't have prime numbers, and 11 is a prime number. So we can't have prime numbers. So 11 is a prime number. And since we can't have prime numbers, we can't take this path. So basically in our complete Dijkstra's algorithm, we have to just ensure that we don't consider any prime numbers. So moving on to the code, the first thing that we do is we pre-calculate our primes. So this is your code to pre-calculate primes using sieve. I won't go into explaining this thing, but you can look up if you want. We just have this is prime array, iterate from 2 to max, and if we have found some prime, we consider all of its multiples and mark them as not being not prime. So basically this is your you pre-calculate all the primes. Then the first thing that we check is n or m prime itself. If either n or m is prime, in that case we don't really we can't really do anything, because uh, either the start point or the end point itself is invalid. In that case, no matter what type of operations we do, in all the cases, we will have at least one prime in our all the operations. So we don't have an answer in that case. Then we begin our Dijkstra's algorithm. Like first thing, we maintain a distance array. All the nodes are to infinity. Then we have the start node n. Initially, we say that all the nodes are to infinity. Okay, max value, yeah, right. So the max value, okay, I missed this thing. So the max value, okay, what is the maximum number of nodes that my graph can have? All right. Now I'm given that n and m are like less than equal to 10 raised to power 4. Sorry, strictly less than 10 raised to power 4. So basically n and m are 3-digit numbers at most. So n can be like something like a 1-digit number 0, 1, 2, or a 2-digit number 10, 11, 10 types, or it can be a 3-digit number 100, 101 or something. But n will always be less than 10 raised to power 4, which is 1, 2, 3, 4. So it will always be a at most like a 4-digit number. So not a 3-digit number, but at most a 4-digit number. And if you look at our operation, it always preserves the number of digits in our number. We can't do like operation on this 0 over here. That's not allowed. You can only do operations on digits which are present in this number right now. So this always preserves the number of digits in our number. And so the maximum number of nodes in our graph, like all the nodes, even if you explore all the nodes, there will be at most like 0, 1, all the way up to 9999. This is the maximum number that you can reach. Any further, and you will need 5 digits, but you can't go to 5 digits with the operation you have from a 1, 2, 3, or 4 digit number. So you'll have at most 10 raised to power 4 nodes. That is your max value. And so we just say that we initialize a graph with 10 raised to power 4 nodes, and let's just say that initially all nodes are at infinity. First, we say that our start node, which is n, we start with the value of n, that is at a distance of 0. Then we maintain a priority queue, which will basically at its top. So a normal priority queue will have the largest element at its top, but we use this template like pair of int vector of the element and the greater of the element. Like greater is the basically comparator. Uh, so pair of int is the integer type, the type that the priority queue is storing. Vector of pair of int is what data type do we want to use, and greater of pair of int is what is the comparator that we need to use. So when we give this greater comparator, this priority queue will be converted to min priority queue. And initially we push the starting node, that is n and distance of n, which is 0, into this priority queue. And then while our priority queue has some node in it, we take the node with least distance from the start node, which has say distance of u. Now it may have happened because of this particular implementation, like it may have happened that the distance of u has been updated and the distance with which we pushed this node into the priority queue is no longer valid. So in that case we continue. Then if not, like if this is the node with minimum distance right now in the graph, we iterate over all the neighbors of this node, check if the neighbor is prime. If it's prime, continue. Like we don't want to consider prime numbers into this whole calculation of minimum distance. And we also ensured you over here that n and m are non-prime. If they are prime, we by default return -1. And then we say that if this distance of v can be updated to a better value, to a smaller value, then we update it and then we push it into a priority queue. And this is like how our complete priority queue goes on. And finally we check if the distance of m is still infinite. Infinite is basically a very large value. We have set it to 10 raised to power 9 plus 7 over here. And if our answer is still like, if the distance of m is still infinite, then we return -1. Basically we never reached m. Otherwise we say that the answer is m plus distance of m. Basically distance of m is all the nodes that you had to visit to come to m according to our edge weight definitions. And the next one more point is how do we calculate these neighbors, the neighbors of the node u. So how do you calculate the dth, like the ith digit of d? What we're doing over here is we iterate over all the bases of n. So if I had, for example, n is equal to 123. Okay, what we do is over here we have base, that is 1, 10, and 100, and our n is 123, 123, and 123. And what we do is we divide n by this base, and in C++, once you divide, you get a lower bound. So basically, we are taking a lower bound of division by base. 123 divided by 1 is 123. 123 divided by 10 is 12.3, but when you take the lower bound, it becomes 12. And 123 divided by 100 is 1.23. When you take the lower bound, it becomes 1. And if you see, you can take a modulo 10 to get the last digit of these numbers. So if you take a modulo 10 of 123, it is 3. Of 12, it is 2. Of 1, it is 1. Basically, this is how you can kind of iterate over all the digits. And then you just check if this digit is 1, so I can convert this digit to like +1 and convert it to 2, -1 and convert it to 0. Now what does +1 and -1 correspond to? Well, +1 and -1 corresponds to being a +100 in n or a -100 in n. So I have this 123. When I do this plus 1, this is my hundreds place. Okay, this is 1 into 100. This represents 1 into 100. So plus 1 would do like 123 plus 100. Minus 1 would do like 123 minus 100, which is the base value. So how do we get our neighbors? We have this the result array. We iterate over all the bases starting from base equal to 1, base less than equal to n. So if base is greater than n, then it like division will lead to 0, and we multiply the base by 10. We get our digit. Basically, we divide our n by base. We take modulo 10. If our digit is greater than 0, then we can decrement this digit. Decrementing the digit corresponds to subtracting base from n. If our digit is less than 9, we can increment this digit. Incrementing corresponds to like adding base to n, and this will basically help us calculate all our neighbors. But we still haven't dealt with the situation where one of our neighbor can be a prime number. We're dealing with it over here. If it's a prime number, don't consider it. And then this is just a normal update of distance. Push it to priority queue once again while the priority queue is non-empty. Take the node with smallest distance and continue this whole process. This is basically the Dijikra's algorithm to calculate minimum distance of m from n. And once we have this minimum distance, we can just return this m plus distance of m. This is our final answer. Okay. Okay. Can you run dry run? Okay, sure. We can just dry run neighbors once. So I'll just consider, yeah, I'll consider rather than 123, like let's consider 230. 230. Okay. Let's consider this. First, we have base of 1 and our n value is 230. So 230 divided by 1, lower bound, that is 230. Take modulo 10, then you have 230 modulo 10, that is 0. So your digit is 0. Now, since digit is 0, you can't decrement this thing. So your d is 0. Decrementing is not allowed, but you can increment this guy to make the digit 1. Now, incrementing corresponds to your base value is 1, so incrementing will correspond to decrementing will correspond to -1, but you can't do that. But you can increment it, so you can do +1, that is plus base. You can go to 231. So our neighbor array will contain 231. Next, our base is multiplied by 10. So this is not a normal for loop usually has +1. This is like n to 10. So our base would be multiplied by 10 in the next iteration, and you would have base is equal to 10. Now 230 divided by 10, the lower bound of this is 23. You take 23 modulo 10 to get the last digit of 23, which is 3. Now, since d is equal to 3, you can decrement 3 to go to 2. You can increment 3 to go to 4. Okay. What does decrementing 3 mean? Well, decrementing 3 actually represents 3 into base, that is 3 into 10. So decrementing 3 is actually decrementing our 230 by -10, that is our base, or incrementing it by +10. So from 230, you can go to 220 or 240. Our overall array will be like 231 from the previous iteration, 220 and 240. And of course, over here we are also checking if any of these numbers of prime are prime number. No, sorry. Okay, actually, over here we are not checking anything. But in the like lower part in the Dijkstra algorithm, we'll be checking if any of them are prime numbers. And finally, your base will go to 100. In that case, like 230 divided by 100, lower bound of this thing, like this is 2.3 is lower bound, which is 2. So your digit is 2. You can either decrement it or increment it. 2 minus 1 is 1, 2 plus 1 is 3. So both of these are like valid values. So you can do both of these things. So you have 230 decrementing this digit represents decrementing by base, that is 100. Incrementing this digits represent incrementing by base, that is plus 100. So 230 minus 100, that is 130. 230 plus 100, that is 330. Your overall array is 231 from the first iteration, then 220 and 240 from the second iteration, and 130 and 330 from the final iteration. So this is how our neighbors array would be calculated, and then in the final iteration, like after this, your base would go to 1000, but this our n is 230, so 1000 would be strictly greater than 230. Our loop would break, and even if you consider like doing anything to this, like this will be like 230 divided by 1000. This is something 0.23's base, so this would be 0. And basically, if you tried doing any operations over here, this would be like operating on this 0 over here, and this is not allowed according to the problem statement, so that's why we are breaking our loop. Yeah, that was what we would do. Okay, this was the third problem. Basically, the third problem involved represent all numbers as a graph. Each node corresponds to a number. Each transition corresponds to a bidirectional edge. Assign weights to the edges in a certain order. Then use Dijkstra's algorithm, and alongside also consider the prime number constraint. And finally, just and yeah, one more caveat was that check if n and m are primes beforehand. And finally, just once you have the minimum distance from the Dijkstra's algorithms, if it's not infinite, then you have your answer as m plus distance of m. Now, moving on to the fourth problem. The fourth problem was count connected components in LCM graph. Okay. In this graph, we were given an array of integers, nums of size n, and we are given a positive integer threshold. Basically, what these two values represented was that they represented a graph of n nodes, where the ith node has the value of nums of I, and two nodes I and j are connected via an undirected edge if the lowest common multiple of this nums of I and nums of j according to our array is less than equal to the threshold. And what we had to do is we had to return the number of connected components in this graph. Connected component in a bidirectional graph is basically two nodes which you can reach one node from the other node by traversing certain edges. Then they lie in one connected component, and so we have to see how many distant connected components there are in these graphs. So let's consider the first sample test case. In the first sample test case, we are given our nums array is 2, 4, 8, 3, and 9. And our threshold value, I'll consider it like TH for short, was given to be 5. Okay. And this is our graph. So basically, this represents a graph with these nodes like 2, 4, 8, 3, and 9. And what I have to do is, like, first let's be clear on what does a LCM mean. So what does LCM of XY mean? Okay, it means the smallest number x which is multiple of both x and y. Sorry, not x. We already have an x over here. The smallest multiple, say m, which is a multiple of both x and y. What this means is that m can be represented as this k1 into x something, and m can also be represented as this k1 into y something. This k1 is an integer, 1 or greater than 1. And so the smallest such number m, so m is basically, this means that m is a multiple of both x and y. and we have to find the smallest such number. If you have the smallest such number, that is the LCM of x and y. So now once we are clear with this definition of LCM, let's move on to our problem. In this, this is our graph, and what our problem said is that you can add an edge between any two numbers, in this case say 2 and 4, if their LCM is less than equal to 5. So LCM of 2 and 4 is 4. Why 4? Because 2 into 2 is equal to 4 and 1 into 4 is equal to 4. So 4 is a multiple of both 2 and 4, and you can check that it's the smallest number that satisfies this thing, and this LCM is less than equal to 5. So due to this, because the LCM of 2 and 4 satisfies this condition, so we can add an edge between 2 to 4. But if we try to say add an edge between 3 and 8, okay, what is the LCM of 3 and 8? Well, the LCM of 3 and 8 is actually 3 and 8 itself. It is 8 3s are 24. But 24 is not less than equal to 5. 24 does not satisfy this condition, so we cannot add this edge. Like, it's not possible to add this edge. And what we have to do is, like, if you had this 2 4, then you have this 3 8 and 9, and actually in the first sample test case the only edge that you can add is between this 2 and 4. So this is the only edge you can add in the first sample test case, and you have to find what is the number of connected components in this graph. A connected component is basically where you can reach from any one node to any another node, and in a bidirectional graph like this, it's basically the number of components in this sense. Like, this is your first component, second component, third component, and fourth component. Why is this a component? Because you can start at 2 and traverse some edges to reach 4, in this case exactly one edge. But even if you had a graph something like this, like one edge over here, 1 2 3, and 1 2 3, and then 1 2, then this graph will like have this one component, this second component, this third component. Basically, we have to find the number of such components in our graph. If the constraints were like, let's consider what would be the most straightforward solution. Well, the most straightforward solution would be I just go from I equal to 0 all the way up to n minus 1, and I go from j equal to say I plus 1, greater values than I, and I check if the LCM of, well, the nums of I and the nums of j is less than equal to threshold. If it is, I can add an edge between I and j, and I can construct a graph, and maybe I can just use DFS or BFS to find the number of connected components, and this would take big of n squared time. N squared for these two loops, like this outer loop will run O of n time, and this will, like, at worst on an average take O of n time. So this will be an O of n squared solution. But unfortunately, we were given that constraints that the number of nodes in our graph is up to 10 power 5. So n is less than equal to 10 power 5, and obviously greater than equal to 1. And also the threshold was up to 10 power 5. So, like, no use over here too. And even the number values, like the nums of I, they were up to 10 raised to power 9. Okay, so these were like pretty heavy constraints. 10 raised to power 9 means that even factoring becomes very difficult. So you couldn't really have anything that was O of n squared. You could either have a big O of n solution or a big O of n log n solution, something like this, or a big O of n into some factor, some constant factor, right? Or at most n root n. Even n root n would be like very big solution. So this brute force approach does not work. This would lead to TLE by analysis. And now we have to think of something. So first, this law that the LCM of two numbers, there's a relationship between the LCM, the GCD, the greatest common divisor, and the product of these numbers. So basically LCM of two numbers, the GCD of two numbers, if you multiply them out, it gives you the product of these two numbers. Well, why is it the case? Let's illustrate it. So consider this: 8 is your 2 into 2 into 2, 2 to the 4 to the 8, and 6 is 3. So 6 is 2 into 3. Now, what is the greatest common divisor of 6 and 8? GCD of 6 and 8 is 2. Like 2 is the maximum guy who can divide both 6 and 8. This is 2. And what is the lowest common multiple of 6 and 8? Well, 6 and 8, like since it's divisible by 8, it must have like 2, 3 times, and it should at least have this 3. So it will have all of these things. So it will be like 2 into 2 into 2 into 3, which is 2 to the 4 to the 8, 3 is the 24. Okay, so this is our LCM. And what happens when you multiply GCD and LCM? So you had this 2, 2, 2, you had this 2 and 3. Your LCM was 2, 2, 2, and 3, and your GCD was 2. Basically, what happens when you multiply out 2 and GCD and LCM is your LCM takes each element exactly once, and your GCD takes the overlapping element exactly once. And when you multiply X and Y, well, every element that occurs exactly once, and these overlapping elements occur twice. And when you multiply LCM and GCD, all elements occur exactly at least once in LCM. Like this 2 occurs here, this 2 occurs here, this 2 occurs here, and this 2 occurs here. And the overlapping elements are taken care of by GCD. And at the end, what you have is your LCM into your GCD is X into Y. So what you can do is, our condition says that the LCM of X into Y is less than equal to threshold. Now, the LCM is a bit tricky to deal with. It's a bit difficult to calculate. And we know that there are certain constraints on the divisors of a number. So any number, like numbers up to 10 power 5, actually 10 power 9 is a very, like what you could say, a large constraint. And we'll see how we can reduce that to 10 power 5. But if you have numbers up to 10 power 5, then the number of divisors is actually less, and it's about less than 10 raised to the power 3 actually. So the number of divisors is actually very constrained. How will calculate the maximum number of divisors? Well, if your number is something like 2 into 3 into 5, 3 to the 6 and 6 5 is 30, then any divisor, like this is 2 raised to the power 1, this is 3 raised to the power 1, this is 5 raised to the power 1. Any divisor will either be like 2 raised to the power 0 into 3 raised to the power 0 or 1. This will have like values between 0 to 1, 3 will have values between 0 to 1, 5 will have values between 0 to 1. For example, you can have 2 raised to the power 0, 3 raised to the power 0 into 5 raised to the power 1. That is, this becomes 1, 1, and this is 5, that is 5. Basically, all primes will have a value in the range of 0 to 1. So you have 2 into 2 into 2, 8 divisors for 30. And you can basically factorize a number into primes and calculate number of divisors. And it can be like check that up to 10 power 5, you have very limited number of divisors. So usually it's a good idea that when you have something related to GCD or LCM, you try to see something related to divisors. Okay, all elements of nums are unique. Will that make any difference in the answer? Yes, it will make a difference, and we'll just look at it shortly. So first, actually, let's get rid of this 10 raised to the power 9 constraint. Okay, so they have given us that nums of I is less than equal to 10 raised to the power 5, but our threshold is actually only up to 2 times 10 raised to the power 5. Okay, around 10 raised to power 5. Now consider one thing. Okay, what is m? So what is the LCM of xy? The LCM of x and y is some number k1 into x, and it can also be represented as k2 into y. And these k1, k2, they are like greater than equal to 1. Since these are greater than equal to 1, then k1 is also going to be like, since k1 and k2 are greater than equal to 1, k1 into x is going to be greater than equal to x, k2 into y is going to be greater than equal to y. What this implies is that LCM of x and y is going to be greater than equal to x, and it's also going to be greater than equal to y. Okay. Basically, this is my 2, this is my 3. Their LCM is 6. 6 is the smallest multiple of 2, smallest multiple of 3. And this multiple has to be like at least this guy or greater than this. It has to be greater than 2, greater than 3. Even in the worst case, if you have like both numbers equal, like 4 and 4, in that case, the what you could say, the smallest multiple, lowest common multiple is 4 itself. This is like the base scenario where your LCM and the numbers are same. And in every other case, the LCM is at least greater than equal to x, and it's also greater than equal to y. Why is this important? Well, you see, our nums of I is given to be less than equal to 10 raised to power 5. But our threshold is all the way up to 10 power 5. But actually what this says is that if I have a certain number x, which is say 10 raised to power 9, no matter whatever uh, this y is, y, it can be any number, like this y can be any number, then LCM of x and y will be greater than equal to x, that is 10 raised to power 9, right? So LCM of x and y will always be at least x, that is at least 10 raised to power 9. But my threshold is 2 times 10 raised to power 5. Like the limit given to me is that my threshold will be at most 2 times 10 raised to power 5 in any case. So this x can never form an edge, because if I want to form an edge from x to y, this edge will have a value of LCM of 10, LCM of x and y, and that thing is going to be at least 10 power 9, because my x has a value of 10 power 9. So its multiple must be at least 10 power 9 or greater than it. But my threshold can only ever go all the way up to 10 or 2 times 10 raised to power 5. So this situation can never occur, and my x, like this 10 raised to power 9 node, this will always be an isolated node. So I can have different graphs over here, but these guys will never form an edge with this 10 raised to power 9. And even if there's like two 10 raised to power 9 nodes, I can't connect them, because this thing once again will have an weight of 10 raised to power 9. So first is that if nums of I is strictly greater than the threshold, then the ith node will be isolated. What does isolated mean? Basically, if the nums of I is strictly greater than threshold, ith node will be a single node, like it will form a component of its own. It cannot form a connection with some other jth node. It can't do this thing, because once it does, its edge weight will have to be at least nums of I, and nums of I is greater than threshold, so you can't like have weight edges with weight greater than threshold according to our problem. Now, what does this allow me to do? Well, this basically allows me to constrain my nums of I less than equal to threshold. And now my constraints, like after I do these things, like what I do is I go over all the nums of I. If they're greater than threshold, then not greater than equal to. If they're strictly greater than threshold, then uh, this ith node is going to be isolated. It's going to form one component of its own. It's going to form an independent component. In that case, I don't need to consider this node I anymore. And finally, I'll only be left with nodes which are like which have values at most equal to threshold. Now my threshold is at most 2 times 10 raised to power 5. So my nums of I will be at most threshold, that is 2 times 10 raised to power 5. And the question that we had, like, will it make a difference if all nodes are unique or not unique? Well, this is the only part where it will make a difference. Like for example, if we had two nodes of 10 raised to power 9 value, then these will be counted as two separate components for any threshold, say up to 10 raised to power 5. These two will be counted as separate nodes. But if you had, say, two nodes of value 10, 10, which is less than threshold, you could just connect them with the edge of 10 and they won't be counted as separate nodes. So if you have values which are greater than threshold and which are duplicates, then they will be counted as twice, and that would be one part where having or not having unique values will make a difference. Other than that, it won't make a difference if you have duplicate values or if you have unique values. Now, after this whole like procedure, what do we have? Our threshold is less than equal to 2 times 10 raised to power 5.
Excuse me, sir.
Yes.
Sir, if the values are equal, so that are satisfying the conditions, no? Like if there are two values 10 and 10,
Yeah.
so that is satisfying the condition that their
Right.
LCM is.
Their LCM is less than equal to threshold. In that case, you can connect them. Basically, you
So
can.
like if in the question it was not mentioned that all the nodes are unique, so
Okay.
then we cannot solve it. Like then also we can solve it, no? Because in future we will be means we will have a we will check it that whether we can take it into a single connected component or not. So like will we be able to solve it or not if there are duplicate values then also?
So basically, the answer is that even if there are duplicate values, the solution that we are looking at right now, it will be able to solve irrespective of whether there are duplicate values or not. And so I hope that you're clear what will happen to duplicate values if they are greater than threshold. Now talking about less than threshold, okay. So what you're saying is like this 10 is less than my threshold value, right? And I have two nodes, 10 and 10. What I can do is I can connect these two nodes and the LCM of 10 and 10 will be 10 itself. This is less than threshold. Okay. Now let's consider two graphs. This graph had all unique values, and let's just say that 10 got connected somewhere over here. This is my first graph, and I had this second graph where I had duplicate values. I had two 10s, and even here the rest of graph was say similar. I connected my 10 to this. What I can do is I can connect this 10 to this and just treat this whole thing as one big component. This whole component as one big 10 value. Okay. So for values of node less than or equal to threshold, even if they are like even if nodes have similar value, even if you have duplicates, what you can do is you can club all the 10s, connect them. You can connect all the 10s and then just consider them as one big component, and all the rest of connections that you will make to say one or two nodes, and you can just treat it as like one big node. And even if you had unique node, basically what we're saying is that if you have duplicate values, you can just club all the duplicate values into one big connected component, and you can have a structure that is very similar to what you would have in case there were duplicate values. There were all values were unique.
Yes, I understood.
Okay. And okay, so right now, up to now, what we have is, so we have this nums of I array, and let's just say that we have dealt with all the values which are greater than threshold. They will form an isolated component, and we have incremented our answer accordingly. And all the nums of I right now are less than equal to threshold, and my threshold is less than equal to 2 times 10 power 5. So now, when we say that my nums of I are up to 10 raised to power 5, and I am talking about LCM over here, okay? So I can add an edge between X and Y when my LCM is less than this threshold. Calculating the LCM is a bit difficult. So let's try to see who can, let's fix a node X And let's try to see what are the different nodes available to this guy. Okay. I have fixed my node X, and let's try to put constraints on what my Y can be. So I have this LCM of X, my X is fixed, and let's just say that I am allowing my Y to vary, and this is the equation that I have to satisfy. With respect to X, with respect to this equation, like what can I change over here? I know this equation that LCM into GCD is equal to X into Y, right? Let's just say that GCD is represented by D. Uh, so basically the GCD is the max divisor D such that D divides X and D divides Y, where this symbol means that like basically 2 divides 4, 3 divides 6, and so on and so forth. This is what this symbol means. So GCD is the max value of this thing. What you can say is that this LCM is X into Y divided by D, where D is the maximum divisor of X and Y. So our LCM of XY less than equal to threshold, this updates to X into Y divided by D less than equal to threshold. Okay. So, right. Now, let's just say now I have three variables over here. One is my X, other is my Y, this is my D, and this is less than equal to, all of this has to be less than equal to threshold. This threshold is given. This X is something I have fixed, so I can iterate over all the N nodes and try to fix it. Now, this D is a divisor of X. Okay, so this D is a GCD. So this is a divisor of X. What I can do is I can iterate over all the divisors of X and try to see how many Ys do I have and do they satisfy it. In that case, I can try to add edges and do all those other things. But okay, let's see. I think these variables are becoming a bit problematic. Let's consider concrete solid values. So let's just say we are considering X equal to 4 and we are considering D is equal to 2. So, and my Y values can be 3 to the 6, 7 to the 14, and 9 to the 18. Okay. And say my threshold is something about 6, the 12, 14, 28, and that is 30. Okay. Let's just say that my threshold is 30. The X I'm considering is 40. My D is 2. This is 6, 14, and 18. These are the nodes I'm considering. So what I'm doing basically over here is I have this X which has a value of 4. I'm trying to add edges from 4 to 6, from 4 to 14, and from 4 to 18. Okay. What will be the cost of this edge? Well, this will be the LCM of 6 and 4, which is again 6 into 4 divided by their GCD, which is equal to 2. So this will be like 3 into 2, 4 is 12. Then the cost of this edge, we can say this is again LCM of 14 and 4, which is 14 into 4 divided by their GCD, that is 2. You can once again, not this 4, you can cancel this out. 7, 7 4s are 28. And the final edge would be 18 to 4, which will be basically 18 into 4 divided by 2, which is 9, and which is 9 4s are 36, which is greater than 30. So this edge cannot be added. Basically what we are saying over here is that I can edge and add an edge from 4 to 6. I can add an edge from 4 to 14. Now consider one more thing. When I can add an edge from 6 to 4, I can add an edge from 14 to 4. So I don't really need to add an edge from 6 to 14. So basically what I'm trying to say is I have fixed this divisor D, so I am considering all the edges x, y such that the GCD of x and y is equal to this divisor. Now, so the cost of my edge will be x into y divided by D, where x and y can be different things, but this D is their divisor for sure, and it's preferably their greatest common divisor. So what I'm saying is, if I have three values, x1, x2, and x3, and x1 is the smallest of them, if I can connect x1 to x2, and if I can connect x1 to x3, it doesn't matter if I can connect x2 to x3. Okay, like, so for example, 4, 6, and 14, and this edge will have, this will have like 7 to the 21 to the 42. So I can connect 6 to 4 with a value of 6 to the 12, 14 to 4 with a value of 14 to the 28. What I'm trying to say is, when I consider all the divisors of this D, the pattern that we are observing is that if I can connect 14 to 6 and I can connect 14 to 4, I can also connect 6 to 14 and 6 to 4, but I don't really need to consider all these edges that are in between. So what I need to do is, I just need to consider the smallest node, that is for 4. Then I can have all my 6, 14, 18, and say 22, and I can just try to connect them to 4. Okay. Why will this be always be like optimal approach? Let's just say that you have an edge from 14 to say some number 18. All right. And this is your 4. You have this edge from 14 to 18. What does this signify? Well, it signifies that 14 into 18 and the greatest common divisor, which we have fixed to be 2, this is less than equal to threshold. All right. What is the smallest number which also shares this greatest common number divisor with 14? Well, since you have edge from 14 to 18, you can replace this 18 by the smallest number, that is 4. So if this equation is satisfied, it implies that this equation, like 14 into 4 divided by 2, this also has to be satisfied. Basically, what we are saying is, if you can add an edge from x to y, and you have some z which is strictly less than y, then you can also add an edge from x to z, given that the GCD of x and y is equal to GCD of x and z. That is something that has to be like guaranteed. If this is the case and this is the case, then as long as you have an edge from x to y, you will also have an edge from x to z. Why is this important? Well, this basically means that you don't have to consider all the nodes. Okay. What you can do is, you can fix an x, you can iterate over all its divisors D such that D divide x. And what you can try to do is, you can try to find the smallest multiple of D, or basically the smallest number. You can try to find the smallest number such that the GCD of x and y is equal to D, and try to add an edge between x and y. Okay. Why will this work? Well, because in any case, if 4 is your smallest number, even if like there's an edge between this and this and this and this and this and this, our result over here, this thing implies that all these nodes, they have GCD of 2 in between themselves, they have GCD of 2 with 4, then they all will be connected to 4. So even in the worst case, even if you don't consider these edges that exist between them, will kind of form this kind of star graph, even if you just consider adding their edges to 4, and we'll end up with a connected component as is required.
Excuse me, sir.
Yes, Abhishek.
Sir, can you please take 1, 2 examples of that conclusion where z is less than y and GCD
Okay,
of x and y equals to? That will help me to, connect better and come to the same page where you are.
right. So let's consider x is equal to 4. And now you have this y is equal to say 7 to the 14 and your z is equal to 3 to the 6. Okay. What is the LCM of, and notice that all of these have like the greatest common divisor over here between any two pairs is 2. So like GCD of 4 and 14 is 2. Similarly for 4 and 6 it's 2, and similarly for 14 and 6 it's 2. So I'll just assume that it will just assume that for all of them the GCD is 2. Now consider adding an edge between so this is your 4, this is your 14, and this is your 6. Okay. What we are saying is, if I can add an edge from 6 to 14, what will be the cost of this edge? Well, the cost of this edge will be LCM of 6 and 14. But we know that LCM can be represented as x into y divided by the GCD, which is 6 into 14 divided by 2. Let's just say that we can indeed add this edge. In that case, this edge will have a weight of 6 into 14. But in that case, since I can add an edge to 14, I can add an edge between 6 and 14. By definition, I can also add an edge between 6 and 4. Why? Because this the cost of this edge will be 6 into 4 divided by their GCD, that is 2. And if you actually compare these two terms, like this is 6 into 14 divided by 2, this is 6 into 4 divided by 2, cancel out these terms, and you're just comparing 4 and 14. So this is like 4 is strictly less than 14. Basically, this edge 1 will have more weight than this edge 2. So if I can add this edge 6 to 14, then I can always add this edge 6 to 4. And similarly with this, consider one more example, like we can have,
Got it.
okay,
But sir, we will try to connect the edge with the minimum weight. No, like
hmm
we will search for the one we can
So
connect with the minimum.
what we are basically what we are doing is that what we're trying to do is we fix this D. Okay, I have fixed my X, I have fixed my D. All right. I want to I want to consider all the Y such that their GCD is D, and this is my edge weight. Now my problem was that there can be a large number of such Y. I can have a very large number of, so from if my say this X was 6 and my D was 2, then from 6 I can go to like 14, I can go to 18, from 6 I can go to 22, and I didn't want to explore such a large number of nodes, because that would obviously, like, I want to optimize my solution. I can't have an O of n square solution. And what this observation above allows us to do is that it says that if you can go to all these nodes, and if all these nodes can come to you because they have a divisor of 2, then it's given that if you have the smallest node of 4, and you can also go up to here, it's given that if you can connect 6 and 22, then you can definitely connect 6 and also 22 to 4. You can connect 6 and 18, you can connect 6 and 18, you can connect 6 and 14, you can connect 6 and 14. So rather than having to check this edge, then this edge, then this edge, what you can do is look at 6, can I connect it to 4? Okay. Look at 22, can I connect it to 4? Okay, I can connect it. Look at 14, can I connect it to 4? And so on and so forth. So rather than exploring the connections in between these nodes, what you can just do is check if this node can be connected to the least number such that the GCD with this number is equal to D, that is 2. All right.
But how we will find that number which we are wanting to connect? Like in this case, we are connecting to 4. So
Right,
how
right.
to find that number?
Okay. Now let's move to that. What we can do is, before like we can just all we have is like we have a bunch of numbers. We have 4, we have 6, and we have 14. Okay. What you can do is you can maintain an array. All right. You have this threshold, so you know that threshold is, say your threshold is given to be 10 raised to power 5, right? what you can do is you can have this array that is smallest multiple, and you can iterate over all the numbers. So first thing I considered 4. Then what are the divisors of 4? Right, 4 can be divided by 1, 2, or 4. I can say that the smallest multiple of 1 is 4, smallest multiple of 2 is 4. Basically, initially, my smallest multiple array, let's just say it has 1, 2, 3, 4, 5, and 6 numbers. Initially, all of them will be filled with minus ones. Once I iterate over 4, I'll fill, okay, 1 has the smallest multiple 4, 2 has the smallest multiple 4, 4 has the smallest multiple of 4. Then next we'll go to 6. 6 has like 1, 2, 3, and 6. These are the multiples of 6. 1 into 6, 2 into 3, 3 into 2, and 6 into 1. 1 has been filled, 2 has been filled, 3 has not been filled. So I say that 6 is the smallest multiple of 3, and 6 has not been filled. Smallest multiple of 6. 5, let's just fill it with minus 1. We don't really have a 5 element over here. And 14, the array size would become too much, but you can imagine filling it with 14. Only 7 would be updated.
Yes, yes.
Okay, so now what you have is, for each D, you have the smallest multiple of this D. Okay, smallest multiple of this D. And what I'm saying is, if you can connect X to certain Y such that the GCD of X and Y is equal to D, okay, in that case, this Y is the multiple of D, right? And let's just say that the smallest multiple of D is S, according to this array. So the smallest multiple of D is S. What will that imply? Well, that implies that this Y is greater than equal to this S. What is the cost of this edge? Okay, the cost of this edge is X into Y divided by the GCD, that is D. What this inequality says that it is greater than equal to X into S into D. Basically, if you can connect X and Y, then you can definitely connect X with S, and by symmetry you can also connect Y with S. So you don't need to consider this edge, you just need to consider these edges. Also, one like valid question would be, how do we guarantee that GCD of X and S is equal to D? Okay, the answer is you don't need to guarantee this. So since GCD of X and Y was D, this implies that your D divides X, your D divides Y, and your D also divides S because you're considering the smallest multiple of D. So you have these three things. Now what that means is that the greatest common divisor of X and S. So D divides X and D divides S. So it's going to be at least this guy D. So for example, let's just say that your X is equal to 4, Y is equal to 6, and S is also equal to 4, right? So your GCD of X and Y is 2, GCD of Y and S is also equal to 2, but GCD of X and S is equal to 4, right? Which is greater than equal to 2.
Sir, what is the significance of S here?
S is your smallest multiple of D.
And D is our GCD.
D is your GCD that you have fixed for now. Okay, now what we are saying is, I can add an edge between 4 and, okay, I think we just, all right. This will be a bit of wrong example. 4 would be a bad example. Just a second. So consider this is 6, Y is consider GCD of 3, and 3 3s are 9, but then that won't work. So Y is 7 3s are 21, and consider the smallest multiple of 3 that you have is 3 3s are 9. So okay, what we are saying over here is you can add an edge between 6 and 21. So what we are saying over here is you have fixed this X equal to 6, and you're iterating over all the divisors of x, and in that you fix this divisor equal to 3. All right. What you're trying to say is, if there is certain y that you can connect to, so if you can connect this x equal to 6 to y equal to 21, and their GCD of 6 and 21 is equal to 3, and you have fixed that 3 too, rather than having to consider all such y elements, what you can do is you can take the smallest multiple of 3, the smallest multiple of 3 that is present in the graph, that is 9. And if you can connect x to any y such that the GCD of x and y is 3, then it's guaranteed that you will be able to connect x to 9, and it's also guaranteed that you will be able to connect y to 9.
Yes,
Why?
yes.
Because x into y divided by 3, your GCD will be your answer. And in the other case, in the worst case, like x into this will be like, sorry, less than equal to x into your s divided by 3. And even if you replace this by the GCD of x and s, so the GCD of x and s is going to be at least 3, because 3 divides x and 3 also divides s. So this is going to be 3 or more. And since this is 3 or more, this thing is going to be like at least this or less than this. Basically, if you can connect x to y and there's this number s, then you are guaranteed that you can connect x and y and s, all these things together. So what this allows us to do is that rather than having to check my x is this, and this, I can just fix an x and a d and check the smallest multiple, that is s. If this is connected, okay, I just move on, and then on certain somewhere I find this y, I can connect it. Even if there's an edge, it's guaranteed that both of these will be connected to s. So I'll kind of at the end up with graphs of this sort, like kind of star graphs, where even if there's an like this edge, I'm ignoring that edge, rather than that we have this edges to the smallest multiple node. Right. Uh, yeah. Any more doubts about
Yes, sir,
the
understood. And then we will push the multiple of D into the our resultant array. Like we took S and we found that we can connect our node X to S. Then
right?
if we can connect our node X to S, then all the multiples above S, that is S plus D, S plus 2D, S
Right.
plus 3D,
All
we
of
will
them can be connected to
all of
S.
them. Then we will push that into our resultant array.
Right. So that was about it, and also a bit of like implementation of this thing. One thing that we can do is we can maybe fill out our like smallest multiple array. We can construct a whole uh, tree. We can construct a whole kind of graph, and then we can just start a DFS from each node. That will be one possible way to do that. But what like I have done in my code is I've used something called disjoint set union, DSU. How it works is will be a bit like too long right now, but basically what it allows you to do is you can have n elements, and you can have two functions, like basically just one function. You can merge two elements I and j. Basically, initially I was in this component, j was in this component, then DSU allows you to merge I and j into one component and get the size of the DSU. Basically, what we can do is I have 1, 2, 3, and 4 initially. Then I say merge 2 and 4. Then my DSU will have 3, 2, and 4 into one component and 3 into one component. Basically, it's a data structure that allows you to maintain components in nodes in terms of different sets. And you can just go on so on and so forth, merging 1 and 3. So you'll have 1, 3 merged into one component, 2, 4 merged into one component, and finally you can just find size to 2. So if that's like clear, I think we can move to implementation part. So this is DSU. We'll just see it later. The first thing, we declare our number of components variable. Uh, and we have one candidate nodes. What we do is first we have this nums array, we iterate over all the elements. If my current element is greater than threshold, then as we have seen, it can never have an edge to any other element. In that case, it will form an isolated component, like this node will not have any edges. So I increment my number of components and don't consider it any further. Then uh, if it's less than equal to threshold, well, I need to consider this element. It may have some edges to other nodes. We push it into our candidate nodes array. Then we once more have like this m value of m, which is the candidate nodes. And here we maintain this smallest multiple array. What smallest multiple of x is going to indicate? It's going to indicate the index of the smallest multiple of x. And so we start with I equal to 0. We iterate over all the elements in candidate nodes, candidate array, and iterate over all of its divisors. If the smallest multiple is like -1, or if the smallest multiple is greater than this element, then we set it to I. Basically, this whole for loop, what it does is what we have done over here. Like,
Sir, can we dry run one that test case which is there in the lead code example?
okay, sure. The 2383, 248391, right?
2483912 and threshold is equal to 10. The second one. That is
So,
actually more
right.
better.
So
Yes, sir.
2, 4, 8,
3912.
3, 9, and 12, and your
Threshold
threshold
is 10.
10, right? So first, like we have our iterate over like 2, 4, 8, 3, 9, and 12, and we have this uh, candidate nodes array. We iterate over 2, 2 is less than equal to 10, so we push it into candidate nodes. 10 is less than equal, 4 is less than equal to 10, push it. 8 is less than equal to 10, push it. 3 is less than equal to 10, push it into candidate nodes, and similarly for 9. But 12 is greater than this threshold, so our num components, which was initially 0, it will be set to 1. So this will basically trigger this condition, num components plus plus. Basically 12 will form an isolated component. Now finally we are left with this 24839 array. What we do is we once again iterate over this 2, 4, 8, 3, and 9 array, and our threshold is 10. We maintain this smallest multiple array. Okay, what we do is we maintain this smallest multiple array, and the size of this array is going to be like the size of threshold, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 over here. Initially, all of these things are -1. Now we iterate over this array. First we find 2, well, and 2 has divisors 1 and 2. We use this function over here to find the divisors. Iterate from 1 all the way, d into d is less than equal to n plus plus. That's how we find divisors. So initially, like 2 has divisors 1 and 2. We look at 1 and 2. 1 and 2 are not set, -1 in our code. So we'll set them to 2 and 2. Actually, we are setting the index over there. Over here, I'll just write it as 2 for better understanding. Then going on to 4, like 4 will be 1, 4 will have divisors 1, 2, and 4. If you look over here, 1 and 2 have already been set, and they are equal to 2, and 4 is greater than 2, so we don't want to update it. But 4 over here, it's not set, so we'll set it equal to 4. Next, we'll have 8. 8 will have divisors 1, 2, 4, and 8. Again, 1, 2, and 4 have been set, but 8 has not been set, and 2 and 4 are less than 8, so we won't update them. Then we have 3, but let's consider 9 for here. 9 will have divisors 1, 3, and 9. 1 and 1 has been already set to 2, so you won't update it. 3 can be set to 9, 9 can be set to 9. Now, if you at last go to 3, 3 will be like 3 will have divisors 1 and 3. 1 is already set, 2 is less than 3. 3 is already set, 3 is equal to 9, but 3 is less than 9. So we are considering 3 over here. So 3 is less than 9, so we'll update this to 3. At the end, basically we have this array -1, 2, 2, 3, 4, -1, -1, -1, and 8, -1, -1, -1, 8, 9, and -1. What does this indicate? Well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This implies that 2 is the smallest multiple of 1 that is present in our array 2, 3, 8, 2, 3, 2, 4, 8, 3, and 9. 2 is the smallest multiple of 1. 2 is the smallest multiple of 2. 3 is the smallest multiple of 3 that's present in our array. 4 is the smallest multiple of 4. For 5, we don't have a multiple, so we have -1. For 6, we don't have a multiple, so -1. 7, we don't have a multiple, so we have -1. For 8, 8 is the smallest multiple in this array that's present. If instead of 8 we had 16, then this won't be 8, rather this would be 16 over here. And so on and so forth. Like basically this array says that for x, what is the smallest multiple present in this array? That is a multiple of x. Okay. Basically, this would be your division of calculation of your smallest multiple. Then what we do is we iterate over all the elements of our candidate nodes, the nodes which are less than equal to threshold, and we calculate all the divisors. Basically, this is fixing the x and fixing the d. That's what we talk about. This for loop fixes our x, the node that we are calculating, and this fixes our d. And so what we are doing over here is 2, 4, 8, 3, and 9. So I have my candidate node. So in code, this is candidate nodes of I, but let's consider x. So I'm iterating over this array. My x is equal to 2. My d can be 1 or 2. All right. If my d can be 1 and 2, when my d is 1, what is the smallest multiple of 1 in my array? Well, I can look up this array and say that my smallest multiple is 2. Okay. My smallest multiple is 2. I try to join x and s. Can I join x and s? Is this LCM of x into s less than equal to threshold? Because according to our theory, like if you can join x and y, then you can always join x and s and y and s. What I try to do is I try to join x and s. If I can do that, I'll always get the best answer. So over here, what we're doing is we're trying to join, like we are iterating over all the nodes, iterating over all the divisors, and trying to join the current node with the smallest multiple of this d. If it is, we call dsu.merge. So let's just iterate over this thing. So for x equal to 2, for d equal to 1, or s is equal to 2, the LCM of 2 and 2 is 2, which is less than equal to threshold. So you merge 2 and 2, but that may not make sense, but we have handled it in code. So if both the elements are same, then we just proceed with likewise. Same for d equal to 2. So even for d equal to 2, you have s is equal to 2, and same thing will occur once again. Then you go to x equal to 4. You go to x equal to 4, the next element. For this, the divisors can be 1, 2, or 4, 4 itself. When the divisor is equal to 1, your s value is equal to 2. Can you join 2 and 4? Well, can you join 2 and 4? Well, what will the value of this edge? Well, it will be LCM of 2 and 4, that is equal to 4. Is it less than equal to threshold? Yes, threshold is 10. So join 2 and 4, that will be represented by merge 2 and 4 operation. For d equal to 2, also we have s equal to 2, and for d equal to 4, we have s equal to 4. So those things can be handled too in a similar way. Similarly, for x equal to 8, we'll have d equal to 1, 2, 4, and 8. For d equal to 1, you will have s is equals to 2. Then what this will do is, for d equal to 1, you have s equal to 2. You will try to join 2 and 8. LCM of 2 and 8 is 8, which is less than equal to 10, which is our threshold. So this is 8. So you can indeed construct this edge. And up till now, our graph will look 2 is connected to 4, 2 is connected to 8. And now, if you consider d is equal to 4, your s is actually equal to 4. So you're now trying to connect x to s, that is 4 to 8. And your edge with 2 to 8 is already connected. So this is like an kind of overlap over here. We have already connected 2 and 4, and we are already connected 2 and 8. And you can try to connect 4 and 8. This will go to, because LCM of 4 and 8 is equal to 8. And you can also have this edge. This won't occur like very frequently in large graphs, but since this is a small graph and all these are like powers of 2, so this happened. Then the next element would be 3. For x equal to 3, you can have d equal to 1 or 3, but for both of them, s is for d equal to 1, your s is equal to 2. What you do is then you connect 2 to 3 for this thing. The LCM of 2 and 3 is 3 to the 6. That is like similar. Then for x is equal to 9, for x equal to 9, and for d equal to 3, s is also equal to 3, so that doesn't really like make any difference. You're just connecting 3 to 3. For x equal to 9, you can have d equal to 1, 3, or 9. Now for d equal to 1, you are going to connect x, that is 9, to the value of s for 1, that is 2. You're going to connect 9 to 2. Can you connect 9 to 2? Well, no, actually you cannot connect 9 to 2, because LCM of 9 and 2 is 18, and you cannot kind of connect 9 to 2. Then you move to d equal to 3. In this case, you try to connect 9 and 3. Can you connect 9 and 3? Yes, LCM of 9 and 3 is equal to 9. Now, one question that you may have is like we thought of something that is, if this connects to this, then this connects to this. Well, if you actually observe over here, the greatest common divisor of 9 and 3 is d is equal to 3, but 2 is not divisible by 3. So our condition that we talked about doesn't hold over here. And yes, I guess that will be how this will hold. Like at the end, your graph would look like 2 is connected to 3, 3 is connected to 9, 2 is connected to 4, 2 is connected to 8. And the merging of 4 and 8 doesn't like effectively doesn't take place, and 12 in and itself is a different node that's counted initially, and finally you have an answer of 2.
Sir, but where did we use smallest multiple wala array? Like we made it, but where
Okay,
did we
okay.
use
So
it?
the smallest multiple is you're using it to get this value of s. So s is the smallest multiple of d. Okay, so right.
Ah,
Just
got it. Yes, sir.
so what you're doing is, when you have x equal to 4, say you're iterating d equal to 1. Now you say that your s is your smallest multiple of d, that is 1, which was set to 2 over there. Then you try to connect 2 to 4. Okay.
Yes.
And yeah. About this disjoint set union, so I think it's pretty late already, but overall what it helps us do is we can basically initialize it with m elements, and we can have this thing that merges two elements, I and the jth element. When you merge them, they are basically represented by a size of kind of a unit of 1. So after multiple merges, at the end, what you have is how many components are there in the graph. You can ask this question to the DSU with DSU.size. That's what we are doing here. One more possible way would be that you could maintain a graph. You could add these things that we are merging over here as edges in the graph. Then you can do multiple BFS or DFS and find the components in a standard way. That would be like one more scenario. Right, I think that was all. Any more doubts?
No, sir, I'll just try to try run once by myself and then it will be
Oh,
more clear.
all right. If there's anything, you can just reach out.
Yes, sir. Thank you, sir.
Okay.
Thank you so much.
So yeah, that was it. Let's